Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And basically, I want to do a recap on what we have discussed so far and then go and introduce new concepts. So a sequence is basically a discrete version of a dense function, all right? So a dense function means its variable is a continuous or real number and can be anything. So it's a continuous variable, and then we have a continuous function. But a discrete sequence or discrete function means we only evaluate the function at the integer, plus integers, negative integers, or 0. And then we said that most of the time we don't use the notation of f of n. If n is integer for sequences, we use a sub n or b sub n. And then we said that one of the main things about sequences is their limit. We want to see if a sequence converges to a specific limit or not. And for example, 1 over n squared, as n goes to infinity, basically as n grows larger and larger, approaches 0. So we said that the limit of this sequence 1 over n squared is 0. This one is Euler's sequence, and the limit is Euler's number, so 1 plus 1 over n to the power of n. So the base approaches 1 from the above, which means the base is always greater than 1. But it's decreasing and decreasing to 1. But then the power gets larger and larger. And any number greater than 1, when it's raised to some power, it grows. So the base tries to, the power or the exponent tries to increase this value, or growing it, but the base is decreasing. So, and the pace of these two cancel each other out perfectly, and this sequence eventually ends up converging to a finite number, which is called Euler's number. All right. And we implemented sequences as a functional interface in Java, and we said that that's a very convenient way because then we can easily define them anywhere in our code using lambda expressions. And we said that one particular type of sequences are recursive sequences, where we define a new term based on prior terms. And then we said that in order to resolve and be able to explicitly find the values of each term, we need to have initial conditions, all right? And the initial conditions, the number of initial conditions we need depend on how many terms we use, how many recursions or recursive terms we have. For example, in Fibonacci, we have we are using 2 of the previous terms to define the new term. So we need to have 2 initial numbers or initial conditions. And then we said that one of the very, very important sequences are called series or partial sums, and then the series and the partial sum of another sequence. So the partial, if we start with the sequence a sub k or a sub I, and we sum its term from some index k, which is usually 0 or 1, to some variable n. So n is variable here. We call this a partial sum for this original sequence an, and we typically denote it by s sub n. And then if this sequence, the new sequence s sub n, or the sequence of partial sums, converges, we say that this series exists, and the value of the series is just equal to the value of the limit, okay? And one of the very important concepts here is that the necessary condition for the series to exist, or for the series to converge, or the sequence of the partial sums to converge to the value of the series or the limit, is that the original sequence or the generating sequence of the series a sub n or a sub k, which is the difference between s sub n minus s sub n minus 1, the difference between 2 consecutive terms of the partial sum. It is basically a sub n. This sequence a sub n must go to 0. The limit should be 0. Anything other than 0, the series does not converge. The partial sum, the sequence of the partial sums, does not converge, okay? And then we said that numerically we can test for convergence by by looking at the absolute error, which is the value of the sequence minus the exact limit, if there is an exact limit. But first of all, we don't know if there is a limit. The series might diverge. So we look at the growth of the series or the change in the series by defining this absolute error in terms of the error sequence. So Sn plus 1 minus Sn. And the relative error is the same thing. Again, we look at how the basically the absolute error divided by what current term grows. Okay. However, there are some well-established tests for convergence specifically for series. So if you have a partial sum sequence from, let's say, 0 to n of some sequence ak, and then we want to know if k from 0 to infinity, basically it's the limit of S sub n, whether it's a finite number or it's an infinity, for example. So whether it converges or diverges. All right. So if this k from 0 to infinity ak exists and it's not infinite, it's a finite number, we call this the value of the series. All right. So we want to test this by just looking at the generating sequence a sub n. And the test is going to tell us whether or not the partial sum sequence converges, or basically the series converges. Here I have put 3 of the most famous tests. The first one is ratio test, or the Lambert's criterion, and it says that take the generating sequence a sub n and find the ratio of a n plus 1 over a n, all right, absolute value, and look at the limit. If this ratio sequence, right, so basically we're generating a new sequence which is the ratio of a sub n plus 1 over a sub n. If this new sequence, the ratio sequence, converges and or maybe diverges, so let's call the limit r. So there are 3 cases. One is r is, let's say r exists, so r is less than infinity. So first of all, r could be greater than or equal to 0, right? R cannot be negative because we are taking the absolute value. So if r is less than 1 and it's obviously greater than or equal to 0, automatically it means that r is a finite number, it's not infinity. And this guarantees convergent. All right. So this, if r is less than 1, we are guaranteed that this sequence, partial sum sequence, converges, or the series converges to a finite number. If r is greater than 1, which can very well include infinity. All right. If this limit is in fact infinity, then we are guaranteed to have a divergent series. The partial sum sequence doesn't converge. If r is exactly equal to 1, then this test is inconclusive. We cannot say anything with confidence or with accuracy about whether or not the partial sum sequence converges. All right, and we have to use, for example, another test. The next test is root test. So root test is important in a few ways, and because when we're dealing with Taylor series or power series, this root test is directly related to the radius of convergence for power series, and that's a very important concept. All right. So again, we take the absolute value of an, this generating sequence for the partial sum, and then take the nth root. So nth root of a sub n. And this is a new sequence, of course, so we can look at its limit. N goes to infinity, and let's call it r. So if r is less than 0 and greater than is less than 1 and greater than or equal to 0, then we are guaranteed that this partial sum sequence converges. If r is greater than 1, which could also include infinity, then this partial sum sequence diverges. We are guaranteed to have a divergent series, and the divergent series means that the result of k0 to summing from 0 to infinity ak is either plus infinity or negative infinity. And if r is equal to 1, then we have inconclusive. The test is inconclusive, and we have to use other tests. The third one is Leibniz criterion, which is typically applied to an alternating series, which means this generating sequence ak, or an basically, has an alternating sign, which is typically means we have a minus 1 to the nth power or something like that in the sequence. All right. So in this case, first of all, obviously we know that an must go to 0, so the limit of the generating sequence must go to 0, otherwise the series is guaranteed to diverge. And the next one is that, okay, so we know that an goes to 0 and an is alternating between negative sign and positive sign. So if for every n is an plus 1 is less than or equal to an, basically an is here we are assuming the generating sequence is -1 to the n, or -1 to the n plus 1 an. So we're assuming that an is basically positive. So you can think of this an here in the conditions as the absolute value of this generating sequence. So here we are assuming that an is basically always positive. We're taking the absolute value. So if an is positive, goes to 0, and it's a decreasing sequence by our definition here. So if it's a decreasing sequence, which means it never goes up, it either stays the same or goes down for every n. Then a sequence, a partial sum, which has an alternating sequence -1 to the n an or -1 to the n plus 1 an. These two are guaranteed to converge. Obviously the difference here is just a minus sign, so it doesn't really matter if we have -1 to the n or -1 to the n plus 1. If the magnitude of the generating sequence is decreasing, and then it's in fact it has an alternating sign, then it's guaranteed to converge. All right, so for a full list of tests for sequences, you can go to this page on Wikipedia, en.wikipedia.org/wiki/convergence tests. All right, and we also said that one of the most important series that are related to functions are Taylor series, and they typically represent smooth functions that don't have singularities, and they are based on an expansion of the function into polynomials around a given point x0, and the terms are 1 over n factorial times the nth derivative of the f calculated at x0. And then as we add more and more terms, this series approximates the function better and better. And then one example here, e to the x is summing from 0 to infinity x to the n over n factorial, and this basically has an infinite radius of curvature, it has an infinite radius of convergence, which means as here we are expanding about x equals 0, okay? But then if we plug any x here, x 100, 200 or something, as we add up this series with more and more terms, it actually converges to the value of e to the 100, for example. All right, that's the definition of the radius of convergence. And when we say that the radius of convergence is infinite, we mean that you can plug any x here, no matter what, this series always converges. And then one of the very, very important concepts that we talked about, it's very important, is the acceleration of the convergence of sequences or series. And we said that if we are starting with the sequence an, which has a relatively slow convergence, first of all, we know that it converges. And then we look at its trend as we increase n, and then we see that it's converging to some number, but it's a very slow convergence. And then we said that if somehow we could start from an and build another sequence bn that also converges to the same number, to the same limit, but then it also satisfies this limit, so limit of bn minus a over an minus a as n goes to infinity. If this is 0, we say that we have transformed a sequence into b sequence such that b has a faster convergence than a. All right, remember, b and a are not the same, but they have the same limit. And if bn has a faster, because we are trying to find the limits, and we want to find it by not going to a very large number of n, because as we increase n, it adds more and more computation cost, which we want to avoid. All right, And we discussed 4 of the most important transformation of the sequence. One of the things that always pops up in this transformation is the notion of delta or difference, discrete difference. So delta of an is an plus 1 minus an, which is also sometimes called the forward difference. And we can also define a reverse difference, which we typically denote by delta bar, which takes an and subtract an minus 1 from it. All right, but whenever we say delta an, we mean forward difference. And we said that binomial transformation, so it takes the sequence A and converts it into a series S, a partial sum from 0 to n minus 1 to the k from n, ak. And then we said that Euler transform, if we have a sequence that has an alternating sign, minus 1 to the n, Euler transforms an to minus 1 to the n, an to minus 1 to the n, Sn, where Sn is basically nth difference of A calculated at index 0 divided by 2 to the n plus 1. And the thing about Euler transform is that it is guaranteed that if minus 1 to the n an converges, the series converges, then the minus 1 to the n Sn, also the series over this sequence, also converges to the same number. So these two series have the same value, the same limit when we look at the partial sum sequence and let n goes to infinity. All right, so these two sequences, when we calculate the series from them, the series are guaranteed to have the same value, they converge to the same number. But the Sn sequence, delta na 0 to over 2 to the n plus 1, this definitely dies off faster than an. Therefore, this series on the right has a faster convergence rate, right? Because one of the things that determines how fast a series converges is how fast the generating sequence an actually dies off. Because an must go to 0, otherwise the series is guaranteed to diverge. And the faster an goes to 0, the faster the series converges. All right. And then we looked at these two very important transformations, which are essentially the same in some sense. And we looked at Aitken's delta squared process, which takes the sequence xn and applies a transformation. We typically call it ax sequence, and at index n, it takes the xn minus 2 minus delta xn plus 1 squared over delta squared of xn. And delta squared means apply delta on delta. So because when we apply delta on xn, it gives us a new sequence, and now we can apply delta on the new sequence again. All right. And we said that Shanks is also the same thing, but Shanks at over an is basically Aitken over xn minus 1. All right. And we said that the idea here is that if we have a sequence, we're summing over am from 0 to infinity. First, we define a partial sum, this capital An, from 0 to n of the original sequence am. And then now we want to see whether or not this partial sum sequence converges. And in order to accelerate the convergence, we apply the Aitken transform or Shanks transform, S of an, which is basically this term. All right. And then we said that the good news is that because the S of an converges to the same number but faster, we can apply Shanks transform multiple times. So we apply S, we get a new sequence. We apply S to the new sequence, we get S squared or S of S. And then this is a new sequence, so we can apply Shanks one more time, get S of S or S cubed. We typically don't go beyond 3 times Shanks because there's a chance that the convergence becomes unstable. So if we apply too many times these Shanks or Aitken transforms, the sequence that we end up with might very well become unstable. And we said that one of the very famous examples are this series that approximates pi, 4 times minus 1 to the k over 1 to the 2k plus 1. This is an alternating series, okay? And we can test it in different ways and confirm that it actually converges. For example, with the ratio test, let's see, if we take the ratio test, we end up with 1 over basically 2 times n plus 1 over 2 times n plus 1, and the limit is 1, so the ratio test is inconclusive. And then but the Leibniz criterion, which we can always use for alternating series, says that okay, this sequence is alternating and its absolute value is proportional to 1 over 2n plus 1, and then this sequence is always decreasing monotonically. Okay, so we have a sequence, we have a series whose sequence is alternating sign and its absolute value is monotonically decreasing, so it's guaranteed to converge. There is no doubt about that. And then we said that we can approximate the error by converting the error into, error is from n to infinity, and we can approximate it by an integral from some n to infinity, and the integral of 1 over x is basically log of x. So the error of this series behaves like log of n, which is very, very slow in terms of dying off and going to 0. Okay, and then we said that okay, if we look at, for example, sum of 20 terms of this sequence, we see that after summing 20 terms of this sequence, we have an error which has about 1 decimal place of accuracy, which is very bad. As soon as we apply the Shanks transform and look at the new sequence, after 20 terms, 20 summations, it has at least 3 decimal places of accuracy. The second Shanks transform brings it up to 7 decimal places of accuracy, and then the third Shanks transform basically gives us an almost exact result. It has more than 9-10 digits of accuracy, decimal places. So we see how the acceleration, all these transforms help. And we said that because we defined the sequence as a functional interface in Java, it means that it can only have one public abstract method, so the rest of the methods should either be static or default. So we added all these transforms as default methods which return new sequences, new sequence objects. The next one of transformations, which accelerates the convergence, is also the very important one, because this transformation, we typically use it all the time when we're dealing with integration, do numerical integration or numerically solving differential equations. And it is called Richardson Transformation. So Shanks and Aitken are good for oscillating sequences, the sequences that have an alternating sign, but they do not work well for non-oscillatory sequences. For example, 1 over n squared, if you look at the series, that is sigma of 1 over n squared, no matter how many Shanks or Aitkens you apply, it doesn't really accelerate the convergence that much. But Richardson transform works very well for non-oscillatory sequences. And then we said that we can define different orders of Richardson. The Richardson of the first order is just n plus 1 times Sn plus 1 minus n times Sn. Remember, we applied these transformations on the partial sum sequence. You can apply it to any sequence, but here we're looking at the series in particular. So we're applying these transformations on the partial sum. Richardson's second order is n plus 2 squared, Sn plus 2 minus 2 n plus 1 squared, Sn plus 1 plus n squared, Sn over 2 factorial, and etc. And here's a Java code that we wrote that implements the first order Richardson. Basically, it's a default method in our sequence interface. And the Richardson, first order Richardson, returns a sequence in object, and we define this very easily using a lambda expression, because when we apply this Richardson on a sequence, the result is a new sequence. So n goes to n plus 1, evaluate the original sequence at n plus 1 minus n times evaluate the original sequence at n. All right. And then we did a very nice example of how Richardson can in fact accelerate the convergence, whereas Aitken or Shanks, they fail miserably at accelerating the sequence. And the example that we used was the series for 1 over k squared. We already know the exact result, exact limit, which is pi squared over 6. And this is a non-oscillatory series, right? The sequence 1 over k squared is non-oscillatory. It doesn't change sign for different k's. And we said that we can estimate the error by converting the error summation into an integral 1 over x squared from n to infinity, which is 1 over n. So the error for this summing up this partial sum of this series behaves like some constant over n plus some constant over n squared, etc. And as we see here, the Aitken after 50 terms, if we apply Aitken 3 times after 50 terms, we only have 2 decimal places of accuracy, less than 2 decimal places of accuracy. But if you apply, for example, third order Richardson, after 50 terms, we have more than 10 decimal places of accuracy. And then another example to signify the behavior or the use of Shanks and Aitken versus Richardson is when we take this exact same sequence, which is 1 over k squared, and we're summing over that. And we apply an oscillatory terms, minus 1 to the k plus 1 over k squared. So this is 1 minus 1 over 2 squared plus 1 over 3 squared, etc. And once we apply Richardson, we see that not only Richardson doesn't help the convergence, but in fact it causes the series to diverge. So if we apply Richardson, the result is a divergence. But as soon as we apply a Shanks or Aitken, we see that this blue one is the original sequence, and the Aitken, the double Aitken and the triple Aitken, they pretty much converge super rapidly to the limit, which is 0.822 something 5. Okay, so when we are dealing with the series of an oscillatory sequence, we definitely use Aitken or Shanks. When we are dealing with a series of a non-oscillatory sequence, we use Richardson. And then we also discussed about where the idea of the Aitken and Richardson in general come from. And the idea was that we can model the behavior of the error as these sequences or the partial sums approach the limit. And we said that for oscillatories, we can model it with the error is basically some number to power of n, right? So it's more like a power model, which is some number to the power. And then for non-oscillatory behavior, which is suitable for Richardson, it's more like 1 over n to some power. Okay? And then we said that, for example, if we have such a model for the error, some number b, and then another number to the power of n, so n is in the power, then we can say that if for large n, an is asymptotic to L, which is our limit, plus a minus b to the n, we can also write the same thing for n plus 1, n minus 1. And then we can solve for L by eliminating a and b. L becomes an squared minus something. So we get this term, which is exactly Shanks. And in order to get this, basically we bring L to the other side, and then we realize that if we eliminate b, basically minus b is an minus L, an minus 1 minus L, an plus 1 minus L, an minus L, and then now we can solve for L. And it's not a quadratic equation, it's a first degree equation. And this is Shanks. Similarly, for the Richardson, we see that we can do the same thing. So if we go back and use this model and apply the definition of the, for example, first order Richardson, here we see that n plus 1, Sn plus 1 minus n Sn causes the error to go from 1 over n to the b to the 1 over n to the b plus 1. So now the order of error goes from b to b plus 1. Similarly for Shanks and Aitken, so if you take this error model, a minus b to the n, and put it into this sequence, which we already know that it converges to L, alright? Then you end up with L plus a some number times another number to the n plus 1. So the order, and this b should definitely be less than 1 for the error to go to 0. Okay. And one of the very famous use cases of these accelerations, specifically the Richardson acceleration, is Romberg integration. So we can start with any slow numerical integration method like forward rectangle or trapezoid or Simpson, and then apply, create a partial sum, define a sequence which is equal to the partial sum of the integration for this method. Here I'm defining a sequence which is the partial sum based on the trapezoid method, partial sum for the integration. And then I apply a fourth order Richardson to this partial sum of the trapezoid and call it the Romberg sequence. And then evaluate the Romberg of sequence at the number of sub-intervals that I have. Okay. And then here's an example. So we looked at f of x equals sine of x, and we integrated this over 0 to pi, and we saw that the forward rectangle has a painfully slow convergence after, even if we divide the 0 to pi interval into 50 sub-intervals, the error has a hard time going down. So the accuracy of the forward rectangle has about 1 decimal place of accuracy. Trapezoid obviously has a faster convergence from faster than forward rectangle. So after dividing the interval by 50 sub-intervals, we get at least 2 decimal places of accuracy. But then as soon as we apply a Richardson on the forward rectangle or a trapezoid, we end up with a much better accuracy. And we also mentioned that here, as you can see, after some number, for example more than 35 sub-intervals, the Richardson kind of becomes unstable. And that makes sense, because the higher the order of the Richardson, the higher the chance that it becomes unstable for larger n. So typically if we increase the order of the Richardson transform, we want to stay to the lower terms, a smaller index, 20, 10, 20. Okay. We also discussed some useful sequence operations. For example, canonical delta is just a sequence that we can define as a static method in our sequence interface. It's 1 only for n equals 0, and for any other n it's 0. Unit step, basically it's 1 for any n 0 or greater than 0, and 0 for any n less than 0. And then we said that the convolution sum of the sequences is defined based on am bn minus m, and we're summing over m. So n is fixed here, is the index of the cn sequence, and m is changing. And we can assume that an and bn sequences are 0 for n less than 0. So here the index runs from 0 to infinity. But then bn minus m, so m also is limited, has an upper limit of n, because as soon as we go b minus 1, b minus 2, b becomes 0. So convolution sum, we define it from 0 to n. Okay. We also define the running average sequence, bn, 1 over the number of terms. We start from an and then add na plus 1 all the way to n a sub n plus m minus 1. Alright, this is some sort of averaging from one point, and it's more like a sequence transformation. Okay. We also discussed the perturbation theory. We said that perturbation theory is a use case of power series, and if we have a hard problem, we can break it down into an infinite number of easy problems by introducing a free parameter, which we typically call it epsilon. And the assumption here is that when we set epsilon to 0, i.e. we end up with an unperturbed problem, we should be able to easily solve it. Okay, ideally we should be able to find a closed form solution. And then once epsilon is not 0, what we do is we write the solution in terms of a power series of epsilon, and then eventually we set epsilon to 1 after finding all the coefficients for this power series. Okay. And one example that I showed here, which is a nice example, is let's say we have this equation x cubed plus x equals 1. and we are asked to find the real root. We already know that the real root should be between 0 and 1, right? Because if it's negative, x5 plus x is always negative. If x is greater than 1, then x5 plus x is definitely greater than 1. And then we said that let's add an epsilon as a coefficient to x term. So x5 plus epsilon x equals 1. And when we set epsilon to 0, we end up with a0 term here, a0 coefficient, which is the solution of x5 equals 1, which is 1. And then we said that, okay, the general solution of this x5 plus epsilon x equals 1, we can write it as a power series of epsilon, and then we found the first few terms, a0, a1, a2, a3, a4, a5, a6. All right, and then in the Java code we actually run the bisection method on this equation, and then we found the exact solution, which is 0.754877, etc. And then we sum these first 7 terms of the perturbation theory, and we ended up with 0.7543. The exact one is 0.7548. So up to 3 decimal places of accuracy, which is a very good thing. Okay. Finally, we also have some useful things to remember when we're dealing with power series and applying the perturbation theory. One is if we add a constant number, capital A, to a series an x to the n, which is a power series, we can represent it with a new power series, and Bn is an plus capital A times delta of n and 0. This is the Kronecker delta. All right. So if n is 0, Bn is B0 is A0 plus A. If n is non-zero, this term is 0, so Bn is An. Similarly, instead of having a constant term, if we have A times x to the p power and add it to a power series, we end up with a new power series, and Bn is An plus capital A delta of n and p. So if n is not equal to p, Bn is An. If n is equal to p, Bn is An plus A. And then the multiplication, exactly the same thing. When we multiply, we end up with a new power series, and the coefficients are the convolution of the original coefficient. All right. And then raising to some power, let's say integer power, it's just multiplying by m times by itself, so it's just the convolution, right? So raising a power series to some integer sequence is just multiplying by itself, so we end up with a convolution. So we can actually raise the sequence to a power that is not integer, let's say 1.2 or -2 or something. Then we can use the Taylor expansion of these basically the 1 plus something 1 plus f to power of m. All right, the Taylor expansion of that. Okay, this was a brief summary so far of all the discussions that we've had on sequences and series. In the next lecture, we look into more of the properties of the sequences and series. So please stay tuned. Thank you for watching, and I'll see you in the next one.